let's say our ethanol is this red spectrum here, and our butanol is this blue spectrum. And I'm actually going to change this so that it is in extinction coefficient units. You need to, well, what's the point? Why are we doing this part of the experiment? Has anyone read what the goal is here?
I don't know. Can't I?
So you've got different data sets, and one of the differences between the data sets is that you've got different initial concentrations in your pure compound, so you'll have different different absorbances and different concentrations, but you'll have the same extinction coefficients. And then the other difference is that you get a different unknown mixture. So what are we trying to do with that unknown mixture that required us to calculate the extinction coefficients?
Determine what it is.
Yeah, exactly. So you're given an unknown mixture with ethanol and butanol, and you're told to calculate the concentration of ethanol and butanol in those in that mixture. And to do that, you're going to use the two-absorber form of the Beer-Lambert law. So you're going to say that the absorbance at a specific wavelength is the extinction coefficient at that wavelength of species 1 times the concentration of species 1 plus the extinction coefficient at that wavelength of species 2 times the concentration of species 2. So you can imagine if you had an unknown mixture over here, so this time we're going to do it on absorbance, you would have maybe some ethanol, some butanol, and that would give you an unknown spectrum that looks something like this, where this point here is the red plus the blue. Oh, what a terrible diagram. And then this point here will be the blue plus the red. Only if these two were exactly the same. So you could surely engineer an unknown mixture where both compounds gave you the same absorbance, but you would have to use their extinction coefficients and calculate what those concentrations should be, and then make your unknown mixture specifically, at which point it becomes not unknown. It's very well known. So normally you'll get peaks of arbitrary height. In fact, most of your data doesn't have distinct peaks at all. Because the butanol has higher extinction coefficient, it tends to dominate the spectrum, and then the ethanol is sort of just a little bit added on. You normally end up with just sort of like a butanol-like spectrum with a sort of extended bit at lower wavelength. So to proceed with this kind of analysis and determine the concentrations of 1 and 2, you need to have the absorbance of your unknown at 2 different points. You need to have the extinction coefficient at 2 different points. And we're going to use the peaks of the ethanol and the butanol for that. So you're going to record the extinction coefficient of ethanol at the peak of, ethanol's this one, isn't it? The extinction coefficient of ethanol at the peak of ethanol, and also the extinction coefficient of butanol at the same point. And then the same thing for butanol, you'll get the extinction coefficient for butanol at the peak of butanol, and the extinction coefficient of ethanol, which is vanishingly small. And that will lead you to make 2 simultaneous equations. So one where you've got the absorbance at 290 of your unknown, is equal to the extinction coefficient of ethanol at 290 times the concentration of ethanol, which you won't know yet, plus the concentration, the extinction coefficient of butanol at 290. I'm just using red and blue. Times the concentration of butanol, which you again won't know yet, and you'll get another equation at 330. So from those, you should be able to solve them simultaneously. Some of you should have been able to solve simultaneous equations in your pre-lab quiz, probably 2 or 3 of you. The rest of you might not have seen simultaneous equations in a very long time. The easiest way to do this is by substitution. So if you're unsure about how to solve simultaneous equations by substitution, you can either Google it. There's 100 good tutorials on how to do this. It's part of the core A-level course in the UK, so there's a lot of good resources for that. And you can also just use an online equation solver. So there's plenty of resources online where people have programmed it in, so you can just put in your absorbance values, your concentrations, and your unknown values, and it'll solve it for you, and I will never know. So have we got any questions about this part of the experiment that remain? Has anyone read through it and has any further thoughts?
That makes sense to me. Is that all you have to do for, is that the post-lab as well? Or
yep. So solving the simultaneous equations is the post-lab part.
Oh, okay. Yeah, that's fine. Perfect.
I didn't want to say it because Neil was in the room, but that thing I told you with the MO diagrams and those in-phase diagrams, that's the answer to question 8. And again, a good answer to question 8 will include one of those diagrams, either the phases shaded in or an MO diagram.
Okay, perfect. Thank you.
Cool. I'll just give everyone a couple more seconds just to think about it and see if there's anything else that comes up.